Welcome everybody to this session. It's our first workshop on the general linear model. So the general linear model underlies some of the models that you've probably built previously in your research, Regression and ANOVA. We're going to have a few workshops focusing on the general linear model. This first one is going to focus on the general linear model in the context of regression. So I just want to go over a couple of basics right at the start. I want to talk about some of the assumptions underlying parametric statistics. It's worth kind of just recapping these. The first one is the assumption that our data are conditionally normally distributed. Now, people very often misremember this assumption and think that it means that the data themselves have to be normally distributed. But actually, what it really means in practical terms is that the residuals associated with the model fitting the data need to be normally distributed. So when we test the assumptions of the various models that we build, one of the assumptions that we're going to test and examine graphically is this assumption here. And what we want to see is that the pattern of the residuals, so the data, model condition on the data, are actually normally distributed. The only test, as far as I'm aware, that actually require the data themselves to be normally distributed are t-tests. And this is kind of what a normal distribution looks like here. So it's only t-tests that require the data themselves to be normally distributed. For the sorts of models that we're building in the context of the general linear model, it's the residuals associated with our model that need to be normally distributed. So the residuals are kind of the error between the model that we've built and the actual data that we're trying to have that model describe. So it'll become clear when we actually look at some visualizations a little bit later, but it's worth kind of just remembering that the data don't have to be normally distributed in order to conduct parametric statistics or build, models based on the general linear model. So the second assumption of parametric statistics is that we have what's known as homogeneity of variance. And all that simply means is that the variance, the variability within our data shouldn't change systematically throughout the data. So we kind of see here, we've got two conditions or two groups. The variance associated with this group is much less than the variance associated with this group. So we can tell on the basis of the width of the distributions of the data. So here we've got an issue. We don't have homogeneity of variance in this case. We've got heterogeneity in variance between our two groups. That's going to be an issue. Here we've got a nice example of the two groups where we've got pretty much identical variances. So we've got homogeneity of variance being met in the second panel here, but not in the first. So we have to check to make sure that the variances within our groups are broadly consistent with each other. The third assumption is that our data should be measured on an interval scale. And what this really means is that the distance between two adjacent points should be the same as the distance between any other two adjacent points. Okay, so a reaction time measure is a good example of that. The difference between 90 milliseconds and 100 milliseconds is the same as the distance between 100 milliseconds and 110 milliseconds if you've got a 10 millisecond scale, for example. So you can't really use R or any other statistical package to tell you about that. You just need to think for yourself, are your data measured on an interval scale? Now, the fourth assumption in the context of the general linear model and with respect to parametric statistics is that of independence. And that really means that the data from one participant does not affect the data from another participant. In other words, the data points are actually independent of each other. And this is important to remember in the context of repeated measures designs because we expect the scores in our experimental conditions to be independent between participants. So that's just a very brief recap on stuff you probably sort of learned when you were undergraduates. So let's look at something else, which you'll probably remember from your undergraduate days, and that's the idea of correlation. So understanding the relationship between two variables. Well, in this case, two variables. You could be looking at more complex sets of variables, but in this case, we're focusing on the relationship between two variables. So, for example, we might have a case of time spent studying on a particular course, particular unit, and subsequent performance on an exam. And it could be the case that there's a positive correlation between the two, where more time spent studying on the studying the unit rather, correlates with better exam performance. It could also be the case that for whatever reason there's a negative correlation, such that more time spent studying correlates with worse exam performance. Or it could be the case there's just no relationship between the two. So there may simply be no correlation between the two variables, where time spent studying just doesn't have any correlation with exam performance at all. So these are kind of three possible correlations, I guess, that we could find with respect to these two variables. And we might represent them something like this. So here we've got exam performance and study time. So study time goes up, exam performance goes up. So we could draw a line maybe a little bit like that. That would be positive correlation. Over here we've got negative correlation, where as exam performance actually drops as study time goes up. And down here we've got simply no correlation whatsoever. It kind of doesn't really matter how long you spend studying an exam with respect to how well you do on the exam. So here's somebody here who spent hardly any time studying, and that's their score on this scale. Over here, somebody else with the same score who spent lots of time studying. So that's a nice example of there being no relationship between these two variables. So if you think back again to variance, when we measure variance or variability in our data set, it's a measure of the amount by which data associated with a variable varies from the mean of that variable. So it tells us something about the deviation or dispersion of the data points around the mean. And we can capture that formally in this equation here. So this really just tells us that we can measure variance by working out by how much each individual data point deviates from the mean. So variance is a concept, again, you'll have learned as undergraduates. With respect to covariance, it's kind of based on this basic variance idea, but in the context of covariance, if two variables covary, then what that means is that when one variable deviates from its mean, we expect the other variable to deviate from its mean in a similar way. In other words, the two variables are kind of moving together. So you can kind of think of covariance in that sort of sense. So let's take a slightly closer look at the data in this panel. So this is again a plot of study time and exam performance, and we can see there's a strong positive relationship between the two, where study time goes up, exam and performance goes up. Okay, so there's a relationship here between the two variables. I should point out, let's get this out in the open now. You can't think of these things as being causal. So this is one of the fundamental misunderstandings that a lot of people have about correlation. Correlation can never tell us about causal relationships, and we'll come on to that later in this workshop. So if we're going to take a closer look at this panel here, we can take our two variables of exam performance and study time and plot those separately for each of our 100 participants. So what I've done is plot the two variables separately in these two plots here by participant ID. The horizontal lines correspond to the means, i.e. the averages of the two data sets. So this horizontal line here corresponds to the average of the exam performance variable. This horizontal line over here corresponds to the average of the study time variable. And I've highlighted four participants, participants 1, 25, 50, and 100. So if two variables covary, if you recall, we were saying that if a participant, say, is below the mean on one variable, then we'd expect them to be below the mean on the other variable. And that's kind of what we're getting when we look at these two visualizations here. So for participants 1, 25, and 50, their scores on one variable were below the mean, and their scores on the other variable were also below the mean, so 125 and 50. Whereas for participant 100, you see they're above the mean on exam performance, and they're also above the mean on study time. So, it looks as if there is some sort of relationship here with respect to covariance, how these two variables move together. And we can actually formalize this by calculating the combined differences. So this equation down here is hopefully familiar to you. This kind of looks a lot like the variance equation, but rather than just focusing on one variable, we're actually focusing on two different variables. We're working out not just variance, but in this case, covariance. So we can actually take our individual data points themselves, study and score. We can work out the average for our study variable, which is 199. We can work out the average for our score variable, which is 79.6. And then for each participant, we can work out by how much their actual data point deviates from the mean of that variable. So for participant 1, study minus mean study is 192 minus 199, which is minus 7. We can do the same for the score that they have in the exam. So we have score minus mean score. So we have score which is 77 minus 79.6, which gives us minus 2.6. We multiply these two numbers together, and that gives us the product here, 18.2, which corresponds for this one participant to this bit of the equation up here. So this symbol here, sigma, basically means it's the sum of all of these for all of our participants. So we can add up for each of our participants all of these products here, and it gives us a sum of 1435.072. So that gives us the top line of the equation. We then divide it by n minus 1. So we've got 100 participants, so n minus 1 is 99 because n corresponds to the number of participants. So we can work out covariance by dividing 1435.072 by 99, which gives us a measure of 14.49568. So we've worked out covariance like that. But one problem with covariance as we've calculated it is that the score we end up with is dependent on the measurement scales associated with our variables. In other words, the covariance value itself isn't standardized. So we want to standardize it. And we can actually divide any value by the standard deviation, and that will give us the distance from the mean in standard deviation units. So if we go back to our equation, we're basically going to put down here on the denominator, the bit below the horizontal line, the standard deviation of our first variable and the standard deviation of our second variable, multiply them together and multiply them by n minus 1. So we can divide our covariance value by the standard deviations of our two variables and write it in this equation here. And this is actually Pearson's product moment correlation coefficient. And it will range from -1, where there's a perfect negative correlation, to +1, where there's a perfect positive correlation between the two variables, with values around 0, meaning no correlation at all. So we've gone from variance to covariance to Pearson's product moment correlation coefficient. But hopefully so far you've been able to see that we've taken something fairly basic, which is variance. It's a measure of variability. We've gone a little bit further. We've looked at covariance. So rather than looking at variability associated with one variable, we've looked at how two variables covary. And then we standardized that using the standard deviations of our two variables to give us Pearson's correlation coefficient, which, I'm sure you've used many times in the past, but it's based on this very simple set of steps in order to get there. So if we plug our standard deviations for our two variables, which we can calculate into the equation, we see that it gives us a Pearson's R of round about 0.9. So Pearson's R is 0.9 for the correlation between our two variables. And that's a pretty high correlation, basically. It means about 81% of the variability in one variable can be explained by the other variable. So we get that 81% simply by squaring this number here. So 0.9 squared is 0.81. Multiply that by 100, and that gives us the percentage of variability in one variable thus explained by the other. Okay, so hopefully you're okay with that. We can pick up on it on the scheduled Zoom call if you've got any questions about this so far. So I want to go back to the point I made earlier that correlation is not causation, and you can't think of it and shouldn't think of it in any sort of causal sense. And here's a nice example, real world example. So there's a high correlation, Pearson's R of almost 0.8, between chocolate consumption in a country and the number of Nobel Prize winners in that country. Okay, so you can kind of look at the visualization here, and you can see as chocolate consumption goes up, number of Nobel laureates goes up as well. Okay, so why do you think that might be the case? Okay, so obviously it would be nice if eating chocolate made you more likely to win a Nobel Prize. That would be a really nice situation. Unfortunately, that's not the case. So what do you think's going on? So what other explanation or what other variables might actually be underlying the relationship? Okay, so if you think about it, chocolate is a luxury product. It's not a staple thing you need in your diet. So chances are the richer a country is, the more its citizens are able to afford luxury goods, nice chocolates, things like that. So the richer the country is, the more chocolate people will be able to afford. But also, the richer a country is, probably the more money government puts into education and training. So we can kind of see that this relationship between these two variables really is better understood if we think about the other variables or factors that could kind of be sort of underpinning it. Okay, so that's a nice example, I think, about really the dangers of thinking that correlation is causation, because it absolutely isn't. And, the media are probably the worst offenders at trying to talk about correlations in terms of causation, whereas they just can't do that. So it's an easy trap to fall into, because very often common sense might suggest that there's an obvious relationship here. You can kind of think of what a causal relationship might be, but the correlation itself doesn't tell you anything about that, so you can't make any claims. And as I said, it's because maybe there are other variables that we don't know about underlying the relationship. Okay, and if you look out there in the real world, you can find spurious correlations absolutely all over the place. There's a great website called Spurious Correlations, which actually lists some of these, bizarre and very entertaining, in many cases, correlations. So here is an example of the number of people who drown by falling into a swimming pool actually correlates with the number of films that Nicolas Cage appeared in any one year. Okay, so the more films the actor Nicolas Cage appears in, the more people seem to drown by falling into swimming pools. Okay, so he's not the best actor in the world, but I doubt that people are purposefully jumping into swimming pools to avoid watching his movies. Okay, that's one example. Cheese consumption. So cheese consumption actually positively correlates with the number of people who die by becoming tangled in their bed sheets. Okay, so the more cheese is eaten in a particular year, the more people die by becoming tangled in their bed sheets. Okay, that's a spurious correlation. There's nothing obviously connecting these two things. Staying on the cheese theme, per capita consumption of mozzarella cheese correlates with the number of doctorates awarded in the discipline of civil engineering in any one year. As mozzarella cheese consumption goes up, so too do the number of civil engineering doctorates. Okay, so again, a completely spurious correlation. I think we're going to have to get away from these food-based ones because I'm starting to feel a little bit hungry at this point. So, lots of nice examples of spurious correlations. I recommend you investigate that website. So as I mentioned earlier, we were talking about how much variance or variability in one variable we can explain by the other. So we can square Pearson's R to get R squared. If we multiply that value by 100, that will be the percentage of variance explained in one variable by the other. So as I said, for the example earlier, on time spent studying an exam score, we got an R squared value of 0.81 because our Pearson's R was 0.9, meaning that about 81% of the variance in exam score is explained by time spent studying. Okay, so we can kind of think of correlation in the context of explaining something about one variable on the basis of what we know about another variable, and that's the basis for regression. So regression ultimately is kind of based on this sort of idea. It'll allow us to predict the value of one variable called our outcome variable on the basis of the value of one or more predictive variables that we know about. Okay, so we've gone from variance to covariance to Pearson's R to regression. Okay, and each step, hopefully, you'll agree is just a small step, and what we're doing in each of those small steps is relatively small itself. In the context of regression, when we have one predictor, we'll call that simple regression. Multiple regression is where we have more than one predictor. What we're going to focus on for the rest of this workshop is just simple regression, where we have an outcome variable and we've got a predictor. So one of the most commonly used regression types is ordinary least squares, or OLS regression, which works by minimizing the distance or deviance between the observed data and the linear model that we're wanting to build. So we're wanting basically to draw a straight line through our data, and we're wanting that straight line to be such that the distance between the individual data points and that straight line is minimized. Okay, it's as small as it can be. Okay, and that's how OLS regression works, and it's important to remember in this case this is all about linear models, so we're talking about linear relationships between variables. So I just want to take a very brief step back from regression per se and talk a little bit more in general terms about what we're doing when we're building statistical models, because most of what we're doing in applying statistics to particular domains, whether it's psychology, biomedical sciences, neuroscience, whatever, we're basically doing model building. So we build a model of the world, effectively, and we're testing to see whether it's a good fit to our data, our observations of that world. In other words, we're wanting to see whether our model captures our data well. So all models, like any sort of model, not just a statistical model, but like a model bridge, a model car, anything like that, all models are an approximation of reality. Some are better than others. There's a great quote often attributed to George Box. I don't know if it's him that actually said it originally, but to paraphrase this attributed quote to George Box, all models are wrong, but some are useful. And I think that's a really key thing to remember in the context of building statistical models with the sort of data sets that we have. They'll all be wrong to a greater or lesser extent, but the best ones are actually going to be useful in terms of explaining what's going on within our data, hopefully fitting in with a nice theoretical framework that you're actually testing when you're collecting your data. So here's an example where we've got up here one of my favourite cars. It's a Porsche 912, so it's actually not a 911, but it's a 912. I've got the real thing up here, and then I've got two models that are better and worse approximations of the real thing. So this one here, that's pretty good actually. What I've done though is slightly transform the image so it's slightly squished, but I think you'd recognize that as being a good approximation of the real thing. Whereas this thing down here is my attempt at actually trying to draw the thing up here. So I'm not the world's best artist, obviously, and this actually wasn't my worst attempt either. So we've got a second model here, which is not a great approximation of the real thing. So what we want to do is basically determine whether or not the model or models that we've built fit our data well. And what we can do is we can actually look to the extent to which our data deviate from a particular model. So we can compare the real data that we have to our model and work out the difference between the two, where the difference, that deviation, we can refer to as the error or residual error. So up here, we can see that the real thing is equal to our first model, which is pretty good, and a tiny amount of error. In the second case, the real thing is equal to our second model, which is pretty rubbish, and actually a large amount of error. So there's a lot of information that's not captured by our model, okay? And ultimately what we're going to be doing in terms of applying this kind of model building to the sort of data sets that we're interested in is we actually want to select the model which will have the smallest error, or in other words, the smallest model residuals, okay? So let's get back to our regression example. So here's a simpler version of our data set. I think there are 8 participants, where for each participant we've got a measure of study time in hours and exam performance. So we can plot data corresponding to these 2 variables for 8 participants. And wouldn't it be great if we could actually draw a straight line through the data points, such that if we knew the value on one axis, we could predict the value on the other axis, say. So imagine there was a perfect relationship between these 2 variables. And imagine you knew that to get a distinction on this unit, you needed to get 80%, say, on a statistics exam, okay? What you would then think to yourself is, okay, if I need to get 80%, what sort of time should I then spend studying for the exam? Okay, so you could actually use what we know about the relationship between these 2 variables to predict one value, which is the time we might need to spend studying, given that we know another value. So that's kind of what we're wanting to do in the context of regression very often. So we're going to draw a line, and we're going to use the OLS method. And this OLS method in regression will provide us with a line that results in the least differences between the values predicted by the line and the data themselves. So we're minimizing the deviation of the residuals. So the actual deviation of the individual data points from the straight line will be minimized. So we're going to plot a straight line that minimizes the residuals. So this is the equation for the straight line in the context of OLS regression. So our y value is going to equal an intercept. So this is the straight line when x is equal to 0, plus this value here, beta, which is the gradient or the slope of our line, multiplied by a particular x value, plus some residual. So this is the difference between the predicted score and actual score of the participant. So what we're wanting to do when we generate a regression line is basically generate or calculate these values here, the value for the intercept and the value for the slope. So that will allow us then to draw the regression line. Okay, so that's what we're going to be doing, and this is what we're going to be doing in R. So how do we determine how good a fit our regression line actually is? So we could work out by how much each observed value differs from the mean of y. We could work out by how much each observed value differs from the regression line. And we could also work out by how much the mean value of y differs from the regression line for different values of x. Okay, so let's look at that visually. It'll be clearer, hopefully. So here's our data again. We've got our 8 participants, each measured in terms of time spent studying and exam performance. So here is the mean as a model of our data. So you might not have really thought about it in this way up to this point, but one particular way of modeling our data is actually in terms of just the mean. So we can draw a horizontal line corresponding to the mean of our data. So this is the mean of in the data set that we have. We could also draw the regression line as a model of our data. So this is the sum of squares residuals. We can then compare the mean and the regression line as models of our data. So this is known as the sums of squares of our regression model. So we can kind of work out these three things. So basically, if the sums of squares of a regression model is large, then the regression model is better than the mean in terms of predicting values of the outcome variable. But if the sums of squares of our regression model is small, then the regression model is not much better than the mean in terms of predicting values of our outcome variable. And we can actually formalize this. We can calculate the proportion of improvement in prediction by looking at the ratio of the sums of squares of our regression model to the total sums of squares. And this is actually R squared. This is the same R squared that we worked out when we were squaring Pearson's correlation coefficient. So this is kind of another way in which we've kind of hopefully connected two things that we kind of know a little bit about already. So in addition to calculating R squared, we can also assess how good our model fit is by using the F-test, looking at the F ratio. So the F-test, the F ratio is based on the ratio of the improvement due to the model and the difference between the model and the observed data. So these are the sums of squares residuals that we talked about earlier. But rather than using the sums of squares themselves, we're going to use the mean sums of squares, which we get by dividing the sums of squares by the respective degrees of freedom. So the F value, the F ratio, is the mean sums of squares of our regression model divided by the mean sums of squares of our residuals. And a good model will have large mean sums of squares associated with the model and small mean sums of squares associated with the residuals. In other words, the improvement of the model compared to the mean will be good and the residuals will be relatively small. So the difference between our model and our data will be small. So we can determine whether our F value is significant by looking up the critical values in an F table. R and any other statistical package will give it to you, but you can also look it up. So we need to work out the degrees of freedom. So for the sums of squares of a regression model, that's the number of variables in our model, in which case, in this case, we've got two. We've got our outcome and a predictor. For the sums of squares associated with residuals, it's the number of observations minus the number of parameters being estimated in our model, including the constant. Okay, so we're going to be estimating the intercept and the gradient. So that means we've got 8 observations. So that means we've got 8 minus 2, which gives us 6 degrees of freedom. And we can look up in a F table, the case where our denominator has got 2 degrees of freedom, our numerator has 2 degrees of freedom, and our denominator has got 6 degrees of freedom. There's 6 there, which gives us a critical F value of 5.143. So for this particular setup, we need to calculate or find an F value that's greater than 5.143 for a result to be significant at an alpha level of 0.05 or less. Okay, so that's kind of how we would do this if we were looking it up in an F table. So let's look at an actual example in the context of R. So imagine that you're a Formula One team director and that you're interested in understanding how the number of points that your team scores in a particular season is predicted by the amount of money invested in the team. So as well as being in charge of F1, imagine you're also a bit of a geek. You also have a secret interest in statistical analysis. You're collecting lots of data. And actually, to be fair, in the real world, sports teams are full of geeks and statistical analysts. I totally recommend you watch the movie Moneyball if you haven't, which explains how various types of statistics were used in the context of baseball. So it's a really good movie to watch. So in a data set that we have, dataset1.csv, we're going to find we have 20 Formula 1 drivers, and they've got the money invested in a particular car, measured in hundreds of thousands of pounds, plus a total number of points you're awarded in a particular season. And what we want to do is work out the simple linear regression equation that captures the relationship between investment as our predictor and points awarded as our outcome variable. So we're going to use the tidyverse set of packages here for a bit of data wrangling and plotting, and we're going to also use the HMISC package for calculating Pearson's R. So when you're doing this on your own machines, remember, set up your new R project folder. Then when you start your new script, at the start of your script, have these two library calls. You will have tidyverse already installed on your machines. You won't probably have the HMISC package installed on your machine, so down in the console, you'll need to do the install.packages command to install the HMISC. So here's our data. So this is our 20 Formula 1 drivers, points scored on the y-axis, an investment in hundreds of thousands of pounds on the x-axis. I should say these are totally fictitious data, by the way. So if you know something about Formula 1 and you're thinking, oh, I'm not sure about these points valued, I'm not sure who that driver could be, it's just the data are just fictitious. So we can visualize the regression line by using ggplot, which is really handy. So we're going to use our ggplot calls. We looked at ggplot in a previous workshop on visualization. So we're going to use dataset 1. We're going to say on the x-axis we want investment. On the y-axis we're wanting points scored. We're adding a layer, a geom layer, such that we want the points themselves plotted. And then we're going to use this geom layer here, geom smoothing function, to plot a linear model, so a linear regression line, basically, and then wanting to add some labels, and I'm just going to tweak some elements in the text as well to make the text size a little larger, and to use sort of minimal sort of aesthetic information in the plot itself. And we're going to set the y limits too, just to make it a bit easier to read. So we've got this regression line, and looking at that, we go, well, yeah, actually that's a pretty clear positive relationship between these two variables. But what we want to do is actually work out what this regression line is. We actually want to build the model, and we want to test the regression line model against the mean as a model of our data. Okay, so we're going to build two models. We're going to build models using the LM function. One of these models will be known as an intercept-only model, where we just use the mean as our as a way of predicting our outcome variable. And the second model is going to be a model where we use investment to predict the outcome, which is points scored. Okay, so we're going to set up our two models. We're going to use the LM function. So model 1, I'm going to say, is a linear model where you have points predicted by, and we just put a 1 here to capture the fact that it's an intercept-only model. And we're going to use dataset 1. So that's our first model. Okay. Our second model, which I'm calling model 1, we're going to use a linear model where points is predicted by investment. Okay. So we've built these two models, and we can actually compare them to each other using the ANOVA function in R, which will give us the F ratio. So we just use the function ANOVA, model 0, model 1. And we'll actually get a comparison of these two models against each other. We're told here we've got our two models. The F ratio is 80, and the p-value is minuscule. So this notation here means that we move the decimal point 8 places to the left, so it's going to be like 0.00000 whatever, 45457, so minuscule p-value, a massive f value, and that's basically telling us that the model where we have our investment as a predictor is a much better model than the model where we just have the intercept or the mean as our predictor. And we can also see that in terms of the model residuals. The residuals associated with the model with our predictor are much, much less than the residuals associated with our intercept-only model, where it's just the mean is used to predict our outcome. So we can kind of see there's a massive improvement as a function of using our model with our investment as a predictor relative to using the intercept only model. We can then use the summary function to actually give us the parameters that we're interested in extracting from our model. So this is our model where we've got investment as a predictor. So we're going to use summary brackets model 1. We're given a lot of information. We're given here, these are the coefficient estimates, so the intercept. This is the beta 0 value that we were talking about earlier. And then this estimate here, 0.241, tells us about the slope of our line. Associated with each of these two estimates is also a t-test. So this test tells us whether or not the predictor itself is significant. And we also have information associated with the r-squared and adjusted r-squared values down at the bottom. So r-squared tells us how much variability in one variable, how much of that is explained by the other variable, whereas adjusted r-squared is an adjusted value which reflects the number of predictors in our model. So as the number of predictors goes up, when we get into the world of multiple regression, or the number of predictors goes up, that adjustment will become a lot more apparent. In the case we've just got one predictor, so the adjusted r-squared value isn't very different from our r-squared value itself. So we've got nice information here about the model that we've built as well. So right at the start, we talked about the importance of checking our model, the assumptions in the context of parametric statistics. So we can actually use a really nice package called performance. So you'll need to do install.packages brackets quotes performance to install it on your machines. And within performance, there's one function in particular which I like called as check_model. And what that will do is give us a visualization of all of the different parametric assumptions that kind of we need to make sure we've abided by. So we can run check model on our model 1. So we get information here about the normality of our residuals and outliers, and it says quite handily dots should be plotted along the line. Looking at that, yeah, dots are plotted along the line pretty nicely. Related to that, non-normality of residuals. Remember, it's important that the residuals are normally distributed. We can look here that the distribution should follow a normal curve, and it generally does. Homoscedasticity, where we'd expect our data should be spread equally around the horizontal line. This isn't too bad. I mean, it's a small data set, so there's going to be a few points here which aren't perfect. It's probably far too small a data set to build a regression model with, but that's not looking too bad. Homogeneity of variance, visualization where I'd expect to see the dots equally spread around a horizontal line, so it's not too bad eyeballing it there. I just want to recall that George Box quote, all models are wrong, but some are useful, so this model might be slightly wrong in a very small number of ways, but is generally pretty useful for the purposes that we have here, which is being able to predict points scored in Formula 1 on the basis of investment in the team. And then if we were to look at this visualization right down in the bottom left, that's going to tell us whether or not there are any overly influential observations in our data set, which might be kind of adversely affecting our model and our model fit. So if we've got one point that has a Cook's distance of 1, which arguably is on the just on the edge of being an overly influential case, but I'm not going to worry about it at this point because, as I said, it's a small data set and it's just on the boundary of what we might consider acceptable. So I would, look at this set of sort of checks here and go, okay, so I'd be pretty happy enough that this regression model sort of was consistent with the assumptions that we need in order to build this kind of model. So what does it mean? Well, we can take this information here in terms of the parameter estimates and actually use this information to interpret what our model actually corresponds to. And if you remember, the investment was measured in hundreds of thousands of pounds. So we have to multiply this value down here by 100,000 to make it interpretable, and this value too, actually. So if we multiply 0.24 by 100,000, then we can actually interpret it. So we would conclude on the basis of this model that the amount of money spent on a driver does indeed predict the number of points they score in a season of Formula One. And specifically, for every £24,000 spent, they will score 1 additional point. And that's kind of how we interpret this sort of output associated with a simple linear regression equation. And really, regression is nothing more than prediction in a sense. We're trying to understand the relationship between two variables. And by understanding the relationship between two variables, that means that in this sort of case, we can predict the value of a variable on the basis of knowing something about another variable and about knowing information about the relationship between those two variables. So the regression itself, hopefully, I've convinced you, is based on, we went from variance to covariance. From covariance, we went to, Pearson's R. From Pearson's R, we went to regression. So again, small number of steps, but we end up being able to build a statistical model in the context of simple linear regression, which actually is really useful because it allows us to understand the relationship between two variables in our data set. And if we're interested in then predicting, we might then be able to predict the value of one variable if we know something about the value of another variable. So regression is really quite powerful, but it's based on, hopefully, you'll agree with me, some quite simple statistical concepts. So that's the end of this video, but what I would now like you to do is work through the rest of the worksheet, where you'll be building up regression models yourselves. And again, if you've got any questions about anything that I've covered in this video, at the scheduled Zoom session, make sure you sort of come to that with any questions that you might have. But otherwise, if you now continue by working through the rest of the worksheet, that would be great.